So I'm Armaan, and I was a part of Basics of ASICS last year, and I'll be studying at MIT next year. Now, my research is on direct pulse density modulated bitstream operators for efficient beamforming. Now, admittedly, that probably sounds like a jumble of random words. So, more simply, I built a camera that sees sound. So this is it. This is a camera that can see sound. But you see, this is actually just one part of my research, which can actually make everything from hearing aids to ultrasound and construction safety and more faster, easier, and more cost-effective. So what is beamforming, and how does it help us focus on specific sounds? Well, beamforming actually uses multiple microphones in order to delay and sum their outputs to constructively interfere target sounds and destructively interfere random noise. With that introduction, let's go back to a little bit before last summer, where I had just built these pairs of hearing aid glasses, which embedded microphones within the sides of glasses. With traditional hearing aids, it's often hard to pick out voices in a crowd. But these use a technique called beamforming in order to focus on one person's voice in a noisy environment. However, I ran into many challenges. Beamforming was slow. Very, very slow. So during PWSI, my friends and I built SuperMic, an 8-microphone beamforming ASIC. For those wondering, an ASIC is an application-specific computer chip. However, we ran into two big issues. First, the CIC filters that are required to convert raw PDM data into traditional audio data are massive and complex, and we couldn't really fit them on the chip. So we had to decrease the microphone count from 16 to 8. Second, delays need to be very precise, like microsecond precision. But without complex and expensive interpolation, we couldn't achieve that. So we have a very limited range of angles that we can choose to focus on. But what if I told you that by directly beamforming raw microphone data, we could dramatically improve speed, efficiency, and precision? In short, this is what traditional beamforming looks like. CIC filters are used to decrease the time precision of the data to convert it into traditional audio. This takes a ton of effort. But then we do even more work to interpolate and increase time precision. These two operations are inherently at odds. So I cut them out, and we end up with this, which dramatically decreases the complexity of beamforming by cutting out redundant stages. Additionally, PDM data is single bit wide, just ones and zeros, and this lets us add all of the microphones in parallel as opposed to sequentially, further increasing speed. To implement this, I built an acoustic camera, a camera that sees sound, which are used in medicine, for example in ultrasounds and echocardiograms, as well as in industry, construction, and more. So for results, you can see that it works. As I move around, it's tracking where my sound is coming from in real time. Admittedly, it wasn't that easy. I am most proud of my perseverance throughout this entire project. It took me over 200 tries just to get the microphone data out to my PC, and even more to deal with linearity, discontinuities, and many more challenges. Now, as for performance benefits, there are many. First, this system decreases computational operations by 16x, and decreases the overall computational complexity by over a factor of n. Meanwhile, it also increases angular precision by 33x. I do plan to keep working on PDM beamforming, and I'm currently building a 48-channel acoustic camera, 3 times the size of this one. And I also hope to revisit my hearing aid glasses once more with this new technique. As for the more further future, I hope to keep working on projects like these, both at MIT and throughout my life. Thank you for watching.